Can we bend an iPhone? Foldable and deformable electronic devices are needed to create wearable displays and non-invasive biomedical sensors. Transparent, bendable conductors are necessary to create such devices. On one hand, in order to conduct current, the transparent film should have metallic characteristics. But on the other hand, in order to be suitable for display materials, the conductive film should be transparent and bendable. Metal sheets, such as aluminum foil, are conductive, but not transparent. And plastic films can be both transparent and bendable, but not conductive. How do we combine these properties? Let's step back. In 1827, a German scientist named George Simon Ohm published a book detailing the relationship between voltage, current, and resistance. This relationship is now known as Ohm's law. Ohm's law states that the current flow between 2 points is directly proportional to the voltage difference between them, and inversely proportional to the resistance of a material conducting current. Thus, current is equal to the voltage divided by the resistance. Voltage is the pressure that forces electrons to flow in a particular direction in a conductor, and current is the flow of said electrons. Or more formally, current is the rate of change of the electron flow in a particular direction. And finally, resistance is the hindrance to the flow of the electrons. Now let's consider a given material. Its conductivity and resistivity are both properties determined by the specific nature of the material. Conductance and resistance, however, are determined by the shape of the specific conductor. Is it slim and long? Is it short with a large cross-section? Well, based on Ohm's law, resistance decreases as cross-sectional area increases, and resistance increases as the length increases. For thin films, which can be considered two-dimensional objects, sheet resistance is the more relevant property. Sheet resistance implies that the current stays within the plane of the conducting sheet. So what materials can be used to create transparent and conductive displays? Well, silver is a very good conductor, and thus silver nanowires have a high intrinsic conductivity and also a high surface area to volume ratio, making them ideal candidates to create high-quality, transparent, and conductive layers. How? When silver nanowires are coated upon a transparent base material, they arrange themselves into a conductive and flexible network. The nanowires are arranged in a random fashion, and if the density is high enough, that means they can touch each other and overlap in enough places for electrons to be able to move freely throughout the sheet. Yet the gaps between the nanowires still remain large enough for the film to be mostly transparent. Moreover, if these nanowires are coated upon a transparent and flexible polymer, that means the entire system can remain flexible. A transparent, flexible, and conductive film can be created by coating a flexible polymer with a solution of nanowires, and this film can be used to create electronic devices such as wearable displays and non-invasive biomedical sensors.